In this video, we are going to go over organic chemistry practice questions. So I've got a number of questions that we're going to answer. So these questions basically are coming from a story sheet. So you can see the questions. So we're going to answer these simple questions. We'll go as far as drawing Lewis structures and give the UPAC names, correcting, identifying errors, determining a number of sigma pi bonds, the type of hybridization, and also sketching the orbitals. Alright, so to start with, one, identify the number of sigma and pi bonds. Okay, so one thing that you need to understand is what is a sigma bond, what's a pi bond, identify how many they are. Okay, so one thing that you need to know is in every bond, and over the type of bonds that you believe you know right now, we have got a single bond, right? Single bond, double bond, and the triple bond. These are the bonds that we have. So in each of these, there is always a single sigma bond. So sigma is always 1, 1. So the first bond is always sigma. Now for the pi bond, in a single bond there's no pi bond. In the double bond, the other one is a pi bond, so 2. And then the other one, the two are pi bonds. And then the first one is a sigma bond. So I would assume that's what the question was asking for. So there's always just one sigma bond in any type of a bond. Pi bond, there's no pi bond in a single bond. There's one in double bond and two in a triple bond. B says we have to state the shape formed in each of the type of hybridization. So types of hybridization: sp, sp3, sp2. So we'll look at this in the should be here. This is how we're identifying the type of hybridization. So I identify the type of hybridization by counting, for example. So for example, if I could give an example um, of this kind of compound. So if you are told to determine the type of hybridization, let's say on C, this C. So I like counting the number of connections. Whether it's a double bond, it's a triple, count it as 1. So 1, 2, and 3. So take the first one to be S, then the rest to be P's. So SP, P. So that gives us sp2 hybridization. That's the shortcut that I use. So equally, if I'm going to focus on this carbon as well, you'd notice something similar, right? sp2 hybridization. Now, so if you look at sp2, sp2 is based on 3 connections, as I've shown you. Now sp is based on 2 connections. Okay, it's a linear, so it's something that's going to be like this. For example, forget about the other 2 carbons. When you look at this carbon has only 2 connections. So this is sp hybridization. So what shape does it form? It's a linear shape. Okay, so sp is linear. I'll skip sp2 and go to the sp2. For sp2, I already showed you an example where you've got a double bond like this, and then you've got hydrogens. So focus on this part alone. Those are 3 connections, something that is coming out like this. What shape is that? So trigonal planar. Okay, and then for sp3, those are 4 connections. So if you did your hybridization, you should be able to remember an example of methane, which has got a carbon and then 4 connections, right? You know this shape, right? I don't want to go in the 3D, but you understand there are 4 hydrogens connected. So this shape is called tetrahedral in 3D, tetrahedral. So that's a shape formed by sp3. Okay, So at least you now identify. You should be able to answer the third question even before we get there. Now, 2 says we have to sketch the 32p orbitals and the sp3 hybridized orbitals. So one thing that you need to know is hybridized orbitals are the orbitals that are used when bonding is taking place. They are the ones that are used. Okay, so they are formed to allow for that. So I'll give you an example again. In a case where we're talking previously about this kind of a bond, let me just draw it again. I like this example a lot because it helps simplify things. Okay, now this is just us drawing a Lewis structure, just showing the bonds. And but in the actual sense, if we're going to go by trying to draw the atomic orbitals, what basically happens here is hydrogen, you know, the element that you have there is, if you're going to write the electron configuration of hydrogen, it's going to be 1s1. Now write the electron configuration of your carbon. 1s2, 2s2, 2p what? So remember, carbon has got 6, so this is going to be 2. So if we're going to draw this as an energy level diagram, to be like that, 1s, 2s, and then may have the 2p there, like that. So let me just show fast. So this is the way it's found. Okay, now not 3 on top, just 2. So this is basically what's there, okay, in the ground level electron configuration. Now when it's activated or ready to bond, there is a movement of that electron here. From here it goes there on the other one, so that you have got 4 4. And then what will happen is these will now will come at the same level. Okay, so the 2s and the other 3p's will come together at one level. Now when they come one level, what basically happens is you've got a combination of one s orbital and 3p's, right? So they get to be called sp3 hybridized orbitals. Okay, that's what basically happens. Now the bonding that is going to happen there, in other terms, is going to be, for the hydrogen it's in s, right? And then for the carbon it's a sp3 hybridized orbitals. Okay, so it's going to be an overlap between an sp3 hybridized orbital and an s orbital. So this is where you find something like this. And I would have to draw it in a better way. So this is for hydrogen, this is for the carbon. Yeah, so this is a demonstration between an overlap between the sp3 and the s orbit of the hydrogen. Okay, so this bond is a sigma bond. So all these are sigma bonds. I said wherever you have a single bond, just know it's a sigma bond. Now I've gone too much into details, just trying to demonstrate this. I hope you've gotten the idea there though. So now the first part, we are supposed to draw the 3 2p orbitals. So 3 2p orbitals. So I've already shown you that there are 3 2p orbitals. I already showed you 2s, and then you've got 3 2p orbitals, right? So a p orbital, the shape is something like this. This is a p orbital, that's the way it comes out. The s orbital is an oval shape. For a p, it's like this. Now for 2p, we know there are 3. Okay, so call one x, other one y, the other one z. So now since they are found at the same part, we're supposed to draw them demonstrating how in 3D. So you can draw the X, Y, and Z. Of course, if we're going to show on the same diagram, it would be something like this. This is one. Then we can have another one along this axis. Then we can show another one along the y-axis. So one is the X, one is the Y, one is the Z. So we can call them 2px, 2pz, 2py. Now others opt to separate them, where you draw the first diagram showing where the y is alone, the other one you show where the z is alone, and so on. So it's still right even in that case, especially that you're going to have maybe only a pen. I would advise you go by the other method where you show separately, show all the three axes and then only draw one. For example, I can only draw the x-axis on this diagram like this, and then label it. This is I can just label down, this is 2px, and then I draw another diagram. I show the y. Of course, I'm supposed to show the other axis, so I'll call it 2py, and then also the other one, draw it along the z-axis. Then you've shown the three 2p orbitals. Okay, so you've seen that they are all based on the shape of the p orbital, right? Because these are the p orbitals. Now we've gone to the sp3 hybridized orbitals. So I did already show you an example of an sp3 hybrid orbital, right? The case where you've got carbon forming all these four bonds. So you just basically go on and just show what basically happens. So where there's carbon, I can just put a dot, and then I can draw something like that. And then we know sp3 forms four connections. So another one there, 1, 2. So we need one more. Okay, so these are four connections. So this is giving us the sp3 hybridized orbitals. So if I'm going to show for the carbon with the hydrogens, if I would go into details to demonstrate the hybridization and even show the hydrogens, I would draw the s orbitals overlapping with these hybridized orbitals. So that now would show that we only have sigma bonds in the sp3, okay, kind of bonding. I hope that makes sense. So if you're going to go for an example of sp, I already showed you it's linear, so it's only this way and also the other way, like that. And then for sp2, which is trigonal planar, would have to go for 3. Okay, so this is sp2. So at least you know how to draw the others even if they were given to you. Now 3 says identify the type of hybridization on each atom in the compound shown below. Alright, so before we answer this question, I just want to let you know that you can check in the description below. You can access our site. So on our site you find that we've got all the videos for all the chemistry topics. Okay, organic chemistry itself is taught from the foundations, the basics, where you learn about all these things step by step, and with several practice questions and even more advanced concepts like naming compounds, the UPAC names, everything is there. On how to come up with Lewis structures, determine the formal charges, every basic knowledge that they need you to understand. And organic chemistry is available on our site, so the link is in the description. Alright, so we're on 3. Now we are identifying the type of hybridization, and I've already covered this earlier. So I said you just count. So take your first counting connection as your S, then the rest to be the P's. Okay, so for the first one, if you look at the OH, so oxygen is better off in the middle, and then so that you can have a bond this side for connected to hydrogen and then connected to the carbon on position 2. Okay, now oxygen is a bit funny. If you look at it, how many electrons are in its outermost shell? You notice that oxygen has electron configuration of 1s2 to s2 and then 2p4, right? So there are 6 electrons in the outermost shell. So in this case, there's one that is taking part in bond formation here. There's equally another one taking part in bond formation there. So they are going to be lone pair electrons, 1, 2, 3, 4. Okay, so there are 2 lone pair electrons, as you can see. So remember, it's supposed to have 6 on its own. They are the ones I've shown in black, and then adding the other 2, it becomes stable, it gains octet. So this in itself entails, if we go for the type of hybridization, would end up with sp3, right? Count 1, 2, 3, 4. So sp3 hybridization is what we are settling for. And then look at 2. So for 2, that's definitely going to be a carbon, right? Now, you need to know that the carbon has got 4 electrons around it, right? So it always wants to form up to 4 bonds. So since there are only 2 there, it implies there are going to be an extra of 2. So whenever we've got 4 bonds forming around individually, it's sp3 hybridization. So therefore, carbon 1, or let me not say carbon 1, let me say number 1, which was oxygen, it's sp3. Number 2, which we've clearly seen to be that carbon, it's also sp3. The third one, third carbon, has got 1, 2, and 3. So all those are counted together. They are giving us 4 bonds already, so we can only count the connections. So that gives us sp2. Okay, it doesn't need any hydrogen because it's already satisfied with the 4 bonds. But the double bond, when you're counting, it's counted as 1 as well. So sp2. Then for 4, oxygen is always going to be sp3 hybridized. So 1 and 4 are the same. So therefore, this oxygen is sp3 hybridized. So there are 2 lone pair electrons there. So 1, 2, and how am I counting? No, how am I counting? Not necessarily sp3. It's not sp3, sorry. So in this case, it's going to be spp, so sp2, because of a double bond that has been formed. And 5, that's the same as like 2. You can see they're similar. So sp3 as well. 6, now 6 is a bit tricky. A positive indicates that there was loss of an electron. Loss of an electron implies there will be no need to form another bond, so it will only form 3 bonds. So 1, 2, and 3. So that would be sp2. 7 is like 2 and 5, so they're all going to have sp3. And then 8 is like 7, so go to 9. 9 is having nitrogen. Nitrogen is having 3 bonds to the hydrogen and these 2 bonds, so that's sp2. So I think I've shown you how to count, and I hope you've gotten it. Applying the same concept to to part 2. I can just expand it so that you can see things clearly. So carbon 1 double bonded to carbon 2, single bonded to carbon 3, single bonded to carbon 4, triple bonded to carbon, which is not numbered, and then to 5. Let's show the hydrogens. So this one needs 2 hydrogens, this one needs 1 to make it 4, this one needs 2, this one is already satisfied, so is this one, that one needs 3. Which ones are numbered? The first one, the second one, third one, the fourth one, and then the last one. So the first one, how many connections? 1, 2, 3. So sp2. The second one, 1, 2, and 3. sp2. 3, 4. sp3. Number 4, 1 and 2 connections. That's sp. 5, sp3. So you count the number of connections. I said take the first one to be S, the rest to be the P. That's the shortcut way of naming or identifying the type of hybridization. So a triple bond as 1, like this, it's different from a case where there are 3 single bonds. Okay? Don't confuse it too. This is taken as 1, that's taken as 3. Okay, so this is where we end with question 3. So ensure you've used the link in the description below to access the full topic, learning all the foundations of organic chemistry. Other topics like kinetics, equilibrium are covered there. Okay, now question 4, we're continuing under organic chemistry. So all the other topics, just in case you want to learn kinetics, equilibrium, the videos are available on our site. The link is in the description below. You should be able to revise with a lot of practice questions and also conceptual based tutorials. So here we're identifying the type of carbon. So we can identify carbons as primary, secondary, tertiary, and quaternary. So based on the number of hydrogens that are connected to them. Okay, based on the carbon, of course we are based on the number of hydrogens that are connected to them. So how do you identify a carbon? So we identify a carbon based on the number of other carbon atoms it is connected to. So a primary carbon is a carbon that is connected to 1 carbon. A secondary is connected to 2 carbons, tertiary is connected to 3 carbons, and then quaternary is connected to 4 carbons. The hydrogens are classified based on the type of carbon they are connected to. So if you look at the fixed diagram there, this carbon is connected to only, it's connected to how many carbons? This carbon is connected to this carbon and that carbon. So it's a secondary carbon because it is connected to 2 other carbon atoms. This carbon itself is only connected to 1. So it's a primary carbon. So you can see that in A, we've already identified the primary, and then we've already identified the secondary. Let's move on. Check this one. It's connected to 1, 2, and 3. So it becomes a tertiary one because it's connected to 3 other carbons. Check this one as well, 1, 2, and 3. So that is still tertiary. Then this one, it's only connected to 1 other carbon, so it's a primary. So we only have a primary, secondary, and tertiary carbon. So in a case where you only have single bonds, we only have 4 types of carbons. Here you're able to easily identify. So all the carbons that are found at the end they are called primary carbons because they are only connected to one other carbon atom. Now if you go inside here, this one is connected to 3, so it's a tertiary. This one is connected to 3, tertiary. This one is now connected to 4, so it's a quaternary. So you can see that in B you have all the 3. We don't have the secondary one, do we? I can't see any carbon that's connected to 2. So in B you only have primary, tertiary, and quaternary. Then for C, that's a primary, 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 primary. Anything at the end is a primary carbon. This one is connected to 3 other carbons. This one to 3. There's this one, and that one. So it's tertiary. So I have tertiary and primary identified already. Then this one, that's still tertiary, connected to 3 other carbons. This one is still tertiary. This one is secondary. So there's no quaternary. There's no quaternary on the C. And then I have to mention that we can also classify carbons, but I don't believe that's the interest in this case. We can identify the types of carbon based on the vinylic and vinylic, based on the double bond. So I have to mention that when you have a double bond, the carbons that are taking part in the double bond are called, they can also be classified as vinylic carbons. Then the ones that are immediately connected to the double bond carbons, these ones are called, that are not necessarily part of a double bond, but connected to the carbon that is taking part in the double bond. They are called allylic carbons. I just had to mention this. I feel it's important. So if you can look at the diagram there, that carbon and this carbon, these ones are vinylic because they're taking part in the double bond. Now this one and this one, they are connected to a carbon which is taking part in the double bond, so these ones are going to be called allylic carbons. So in case I ask you to classify carbons based on that, vinylic double bond, allylic connected to a double bond carbons, of the vinylic carbons. So here you can also identify on D. So whenever you have a cycloalkene or alkane, all you have are secondary carbons because they are all connected to 2, one on the left, one on the right, as you can see. This is a secondary, because there are 2 carbons on either sides. Now this one is not, because it's having 1, 2, and 3, so it becomes tertiary. So of secondary, tertiary. Now because of the terminal one, we also have a primary present. Yeah. So that's it about 4. Simple and straightforward. Now 5 is dealing with identifying amine, sigma, and pi bonds in each of the compounds. Now I already did explain that in every single bond, in a single bond, there's a sigma bond. In a double bond, there's one sigma. So in every type of a bond, the first one is a sigma bond, the rest are pi bonds. So do the counting. So a sigma bonds, so for sigma it's easy, just count the number of bonds that are part of that compound. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 sigma bonds for the first one. Now for the pi, count. For a double bond, count once. For a triple bond, count as 2. So there are only 2 double bonds here. So each double bond has got 1 pi bond. So therefore we only have 2 pi bonds for the first one, since there are only 2 double bonds. In each double bond there's a single pi bond. For B, pause the video and try it out. So 1, 2, 3, 4 plus a hydrogen, 5. So we've got 5. I know some of you can't count the hydrogen because it's not expanded, but it can be expanded, like you can see this one. Even that one can be expanded. So 5. And then the number of pi bonds. So we've got 2 which are part of the triple bond because 1 is a sigma, and then there's 1 there. So we've got 3 pi bonds, surprisingly. Then the last one. So it's tricky where they've not expanded the hydrogens, but take note of them. So I'll first of all ignore them. So I'll count the bonds inside. 1, 2, 3, 4, 5, 6, 7, 8. So the ones that are visible by expansion are 8. Now I have to add the number of hydrogens. So 3 plus 3, 6, 9, 12, 15, 16. So 16 plus 8, 24 sigma bonds. The pi's, there's only one double bond there, so there's only one pi bond. So I believe you now know how to. This is very simple and straightforward. This is what organic chemistry is. There's nothing complicated about organic chemistry. Everything is simple and straightforward. Now, if you look at 6 here, we're identifying the errors that are there in terms of the names. How were the names given? Were there errors there? Okay? So we have to identify the errors that were there. So this requires us to understand the UPAC nomenclature. So this is available. Check the link in the description to understand more. Okay? So just go to our site, you understand more in detail on how to name different kinds of compounds. Okay? So let's go on. Let's look at this. A. 2,2 diethyl 33, dimethylbutane. So just one simple tip that I would give you, even without wasting a lot of your time, is I suggest every time you're looking at such, you expand the compound. Expand the compound. It will be easy for you to spot out the mistakes in the way the name is given. So if we are saying dimethylbutane at the end, it means the point name is 4 carbon atoms. Okay, so I've drawn the parent structure. Now on carbon 2 we have diethyl, meaning that there are 2 ethyls. Ethyl comes with 2 carbons, so now there are 2. And then on the third position we have 2 methyls, like that. So I'm not showing the hydrogens for simplicity's sake. Okay, so is it true that the longest structure is butane, or we can say a longer one instead now? So if you look just straight here, 1, 2, 3, 4, 5. So that's already longer than the parent name we're given. You can also 1, 2, 3, 4, 5. That's still longer. So therefore the name can't be butane as a parent name. We have to change the name. Now it's either we choose this or we choose a straight one, since they are all equal. The rules, the UPAC rules are, in a case where this and this are equal, go for the one which is having more subchains. So if we just go straight, we're only going to have 2 subchains, this one and this one. Now if we turn, the subchains are going to be a lot, which is okay. That's what the UPAC tells us. We should go for the one having more. So this one, this one, this one, and this one. So 4. So we'll go for that. Start counting from a side which will give you lowest positioning. We have to start from here because it will give us 1 and 2. 1, 2, 3. Now if you start on top, the first substituent is going to be on 3rd position, so we'll start from there. So 4 and 5. So it shows on position 2 we have 2 methyls, so 2, 2 dimethyl. And then on position 3, in fact I have to be careful, I don't necessarily have to say dimethyl already. I can see that on position 3 as well, there is another methyl there because of a carbon, so trimethyl. And then on position 2, sorry, on position 3 again, there's also two bonds there, two carbons, sorry. So on position 3 there is ethyl, so 3 ethyl. And then the parent name, we've got 5 carbons, so it's pentane. There's no double bond there, so it's not pentane. We can now combine the name together. So the name therefore becomes out is alphabetize. Ethyl comes first, so 3 ethyl, and then 2, 2, 3 tri methyl pentane. So that's how you go about this, and we're going to go up B, C, and D, how you're going to be solved. All right. So these questions are all answered, and if you want to access the solutions of this tutorial sheet and some other more solutions, just visit our site, okay, or you can visit our Patreon page for solutions to all these questions. So starting from question 6 itself, going up to the drawing Lewis structures, providing the UPAC names, with learning the topic in full. Everything is available on our site. The link is in the description. You have access to PDF solutions as well. Okay, so what are you waiting for? Just visit our site. You have access to all these solutions. Thank you very much for watching this video. This is where we end.